Understanding light passing through a double slit screen. Here we have a red light passing through a screen and projected on a back screen. Since this light is passing through two slits, it should be expected the projected light looks like this, but in reality looks like this. Diffraction and wave interference can explain this result. This is a diagram that represents this picture. This red light will diffract when passes through the slits. Red light as a wave will split into two identical waves. Both waves are coherent. They have the same frequencies and wavelength. They interfere with each other between both screens. So now we have a section of crests that meet with crests, and the crest meeting with crests, crest meeting with crests will produce area of constructive interference. And between we have crests meeting with the trough of the other wave, and we have area here of destructive interference. The result wave will be just like this. So now we have areas of bright color, bright, and bright spots. And we have areas of dark, and dark due to destructive interference between both waves. So this explains the shape of the projected light with alternating bright and dark spots. So these spots we are going to call fringes. So the bright fringes are more pronounced in the center because the wave here is taller. Now let's understand why the waves, the adjacent waves, they are not as taller as the center one. So instead of having the semicircle waves, let's just draw one single wave passing through this slit and hitting the spot right here. So the wave that comes from this slit to arrive at the same time, we need one extra wavelength for this happen. So here we have one wave, and here we have one extra wave. So since they are coherent, they have the same wavelength and frequencies, so we can add the vertical displacement in this case of amplitude. Both amplitudes are positive, both amplitudes are negative, so we are going to have a taller wave, but one wave is behind, so that will produce a smaller or not as tall as the center one when both waves they arrive at the same time. So that explains why we have this shape. Now, let's understand the dimensions of these, all the variables involved in the double slit type of problems. So here we have the light. They have a specific wavelength. Is going to pass through those two slits. So the wavelength of the incident light is the lambda, and the A is the distance between the two slits or opening on the double slit screen, and the X is the fringe separation on the projected screen, must be the distance between two adjacent bright fringes or two adjacent dark fringes. And D is the distance between the double slit screen and the projected screen. So now you're ready to solve this question related to a light and a double slit. Question overview. A and B is asking to write what is a longitudinal wave and the principle of superposition. And the core of this page is this question right here, where a light is passing through a double slit, and is asking to use a formula to calculate the wavelength of this light. And then finally is asking what would be the change of intensity of the light if one of the slits will be reduced. Question 4a. By reference to the direction of propagation of energy, state what it meant by a longitudinal wave. So longitudinal wave is a type of mechanical wave that required particles to carry its energy. So those particles, they vibrate parallel with the direction of propagation. If the propagation going this way, the particles are vibrating back and forth in that direction. And because the vibration, the particles bump into each other, and for the reason, carry the energy of this wave. Here we have two independent waves, wave A and wave B. They are traveling in the same medium at the same time. So when they meet, we can add the vertical displacement for each wave, and the resultant wave will be this red one. So that's the principle of the superposition. So to state the principle of superposition, we can say that when two waves overlap or meet, the resultant displacement is the sum of the individual displacement of each wave. Now let's go to the core of this question. The wavelength of light from a laser is the term used in the apparatus shown in this picture. The light from the laser is incident normally on the plane of the double slit. The separation of both slits is 3.7 times 10 to the negative 4 meter. The screen is parallel to the plane. This screen is parallel to the plane on the double slit, and the distance between both screens is 2.3 meters. A pattern of bright fringes or bright spots and dark spots is seen on this screen. The separation of adjacent bright fringes of the screen is 4.3 times 10 to the minus 3 meters. Calculate the wavelength in nanometer of the light. To solve this problem, we are using this equation. The wavelength of the light is equal to the separation between both slits. So this is my A, times X is the distance, the separation of two adjacent fringes. Could be too bright or too dark. So in this case was provided. So I draw here on this screen bright, dark, bright and dark, just for you have a feeling what's going on here. So between two bright fringes, the distance is this. The distance between two dark fringes will be the same value. So it will not matter if it's between two bright fringes or two dark fringes. But in this case, was given two bright fringes. So bright. And D is the distance between both screens, which is 2.3 meters. Now that I have identified all the variables A, X, and D, I can make all the substitution in this formula and use my calculator to find this result. So the way that you do is 3.7 EE negative 4 times 4.3 EE negative 3 divided by 2.3, and we have this value. They're asking in nanometer, so nanometer is 10 to negative 9. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So our decimal place will be right here, 692 times 692 times 10 to -9 meter. So this is our prefix nano. So that is why the result is 692 nanometer. The final question is asked is give you a different scenario here. The intensity of the light passing through each slit was initially the same. The intensity of the light through one of the slits is now reduced. Compare the appearance of the fringes before and after the change of intensity. With two slits equally spaced here, so the light is passing through and is going to project on the other screen section of bright, dark fringes. Something like this. That's what you should be expecting. So we have a brighter in the center, and then we have between, we have dark. With both slits on the original size, a wave A and wave B being coherent and have the same wavelength and frequency, the interference between both will be a complete constructive interference. So the vertical displacement here is going to be kind double, and the vertical displacement here will be also double. If when those two waves they are out of phase, which means that the crest meets with the troughs, so because they have the same size, so the result will be a flat line. Likewise here, one is negative, one is positive, and we have a flat line. Now let's take a look when one slit is reduced. So let's say slit B, or the wave produced by a slit that was reduced, let's call the wave B. So we have here the wave A, original size. Wave B will be reduced because you have now the smaller opening. So if they are in phase, when we add them, so will be a wave that is less tall as this one here, because this vertical displacement is less. Now when they are out of phase, so because this is the original one, the original size, and this one is the reduced size, so when we add the vertical displacement here, so this is taller than that, is not the same amount, so the result will be positive because this one is greater than this, so it will be a positive vertical displacement, and this will be a negative vertical displacement. So you'll be a less a wave that is with amplitude reduced, contrary of this one here that will be completely destructive. This is not going to be completely destructive. So we can answer this question in two ways. One is there is no longer complete destructive interference. There is no longer complete destructive interference. The amplitudes no longer completely cancel. So the dark fringes are lighter. So here we have the original one with bright fringes and dark fringes between. And now we don't have those dark fringes. Now we have a kind blend together. All these fringes blend a little bit together, but you can identify a brighter light in the center.